In this video I'm going to discuss self-induction, mutual induction, and then transformers. So we know that a current carrying wire has a magnetic field around it. If it's creating its own field, it has its own flux. So the current changes, as in when the current starts to flow or decides to stop flowing when you press the switch, there is a change in the flux, change in the field because there's a change in the current. You will have a self-EMF, self-induced EMF, trying to oppose this change as well. So that means, simply put, that when I start my current flowing, let's say in this direction and down the coil, because of this self-induced EMF, it will try to push back. It will be a bit slower. Eventually the current will become steady and then the self-induced EMF will stop because the current is steady. Only when the current stops flowing, that's when you will have another self-induced EMF. The current is trying to stop and the self-induced EMF wants to keep it going. So this causes a small delay when you switch a light bulb on or when you switch the light bulb off as well. So that's self-induction in the wire that carries the current. The faster the change, the greater the change in flux, which means the greater the induced EMF that will oppose this change. Okay, it only happens when it's changing. It doesn't happen when the current is constant, because when it's constant there's no change, so then there's no flux change, there is no induced EMF. Mutual induction is the same idea. If I have a coil on the left hand side, and even if there's a space between the two, and I have a coil on the right hand side, because of this change in flux when a current changes, for example switching the current on and off, or using AC because that goes positive to negative, that will create a constant change in flux, change in field. That will induce a current in this side as well. It will be the opposite to the change. So if it's getting stronger, it will be getting weaker. It will, as in, if it's going, let's say, clockwise, this will be going counterclockwise. If it's going counterclockwise, this will be going clockwise. Opposite direction. Not too important, you just need to know that it will create a current. This lamp will turn on and off as this is changing. We call the first coil the primary coil. The second coil will be called the secondary coil. And this is the formation of a transformer, which we'll get to. If it's a steady current flowing, what's going to happen in the secondary current? Well, as you know, if my fingers are coming down the page, like this, if I take my fingers down the page, my thumb will be pointing to the right. However, it is constant. If it's constant, there is no change in flux, there will be no induced voltage. Nothing will happen. However, in example 2 now, I have opened the switch. That means the current will decrease. Opening the switch is breaking the circuit. The current will stop moving. So that means, in this case, we know that the current is getting weaker. That means the induced field will be in the same direction as we discussed using Lenz's law previously. So it will be in the same direction. The induced field was going to the right as I drew in the previous picture, and that means the induced field will also go to the right. And again, in this case, if it is going to increase the current, we already established that the field is going to the right because the current is coming down. My fingers are down, my thumb is to the right. It looks like this. My fingers are down, my thumb is to the right. And we find that this is getting stronger, so it will oppose the change. It will be induced in the opposite direction. Okay, this is how transformers work. You have a primary coil, a secondary coil. One will have more turns or less turns than the other, and that can increase or decrease the voltage that you end up getting at the end. So we use them. We have energy generated at your power plant. It will go into a transformer so that it can be transported very far away to the nearest towns. And then on that side you will have a lot of voltage because this side will be a step up. I will increase the voltage so that the electricity can travel very, very far. When you get to that side, you will have hundreds of thousands of volts. It's not good, it's dangerous for you. So they have a step down transformer. This is step up and this is step down. That will reduce the voltage in something a little bit more manageable, and that can reach to your home, and then you can watch TV, and then your dog can also watch TV. That's how step down transformer works. So step up, it transforms or changes low to high. Step down is the opposite, it changes high to low. You can see that on a diagram. If you have more turns in the secondary coil, this must be step up. And this has got more turns in the primary coil, less in the secondary, this must be step down. So looking at this one over here, you see that we have the input voltage of 240, output is 480, so the output has increased. I have a bigger voltage. This must be a step up transformer. You'll find that this doubled, so my primary coil was 100, the secondary coil will double, it will also be 100. Another example here, we have 200, don't know this one, but I do know that we have 12 turns and then only 6 turns. This is half of this. This must be stepped down, and half of that means that will be 100 on this side, 100 over here. So it gives us a formula. You don't have to predict yourself every time. We can use a formula. NP equals VP, NS equals VS. So NP over NS equals VP over VS. You can also say NS over NP equals VS over VP. You can flip it as long as you flip both sides. The S's stay together and the P's stay together. You could even write it the other way. You can write VP over VS equals NP over NS. It does not matter, because when you cross multiply, it will end up being the same thing anyway. You cross multiply, you will get the same. Cross multiply, you will get the same. So here is an example. What we're going to have here is that we have this, but not this. So we can set up the formula. So we're trying to find VS. Oh, this is talking. There we go. So we're trying to find VS. We can cross multiply. We'll have 200 times 230 equals VS times 2000. And then you will divide by 2000 at the end when you rearrange. And that means the final answer will be 23 volts. We have plenty of examples on this, more practice that you can do in your own time as well. So step up and step down, and it's a little summary here. Step up will increase the voltage, it'll have more turns. Step down is the opposite, decrease the voltage, less turns. The power will be the same in an ideal transformer. In an ideal transformer, no power is lost. So you can say primary equals the secondary. If you remember the formula, P equals IV, PIV, P equals IV, you can put that here, IV equals IV. And if I put this arrangement into my formula, it will actually be opposite. When you take the S to the other side, it will go on top, it will become IS over IP. So it's the only part that's flipped. This part is flipped. This is VP, NP, IS. VS, NS, IP. That's the only difference. So you can use these four to calculate the current, or you can use this and this to calculate the current. You can use any selection. So I could do VP over VS equals IS over IP. I could do NP over NS equals IS over IP. It doesn't matter which I choose. We do have energy losses. The coils get hot. The iron core in the middle will also get hot. There will be sound coming. Power will be lost as heat and sound. So it will always be less than 100% efficiency. And we can find the efficiency. We can find the efficiency by doing P out over P in, whatever power I get at the end of it, divided by the power that was put in, and then you times it by 100 to make it into a percentage. So the losses that you'll get in the transformer core, eddy currents, flux leakage, the circuit losses, the coil and wires of course have a resistance as well. They get hot, so we will lose energy in many ways. One thing you need to know about energy getting lost in eddy currents is that if you have your iron core, electrons, this is iron, this is a metal, it's a conductor. Electrons can flow freely around this iron. So as it flows around, you're getting more heat loss. So we can decrease this by cutting it up into smaller pieces, and we call it laminating the core. We can cut it into a small piece and put some insulation in between. So now the electrons can only flow in certain parts. They cannot travel all the way to the end. They cannot do that. So that's one way to help. We did a little Kahoot on this. Here's a little comparison table that you can read through and just compare the two different types of transformers.